Good morning. In today's class, we will learn about minimum cost spanning tree using Driscoll's algorithm. As we all know, every spanning tree of n vertices will have n minus 1 edges. The problem here is to select n minus 1 edges such that the cost of the spanning tree is minimum. In the previous session, we have seen the method of obtaining minimum spanning tree using Prim's algorithm. Now in this session we will learn Driscoll's algorithm to find the minimum spanning tree. Here the general procedure is let G is equal to VE be a directed graph. This algorithm selects n minus 1 edges one at a time. The algorithm selects the least cost edge UV from E and deletes the edge UV from E. Then it checks whether the selected edge UV results in a cycle when added to the list of already selected edges to form a minimum spanning tree. If no cycles are formed, then selected edge is added to the list of edges selected to form a minimum spanning tree. The selected edge which results in a cycle is neglected. The procedure is repeated till all n minus 1 edges are selected and there are no more edges to consider. If n minus 1 edges are selected, the selected edges result in minimum spanning tree. Otherwise, the spanning tree does not exist. The two functions which are essential for the design of Driscoll's algorithm are find of u and union of ij. Find of u, if u is a node in a tree, this function returns the root of the corresponding tree. Consider the set 1, 4, 8, 6 and 2, 3, 7, 5. These two sets represent two different trees. The first item in each set acts as the root of the tree. And similarly, union of ij. Let C1 and C2 be two. Let C1 and C2 be two trees. If I is a tree in the tree C1 and J is a tree in the tree C2, this function merges the two trees C1 and C2 into a single tree. Now we will implement this using an example. Now there is a graph and we have to construct a minimum spanning tree for this graph. And as you can see here, I have initialized a forest of 6 trees. 1, 2, 3, 4, 5, 6. Edges are not shown in the heap. Then in the first step, I have selected the edge with the lowest cost, that is 2 to 5. Find 2 is equal to 2 and find 5 is equal to 5. Union of 2 comma 5 will result in f is equal to 1, 2 to 5, 3 to 4 and 6. Here one edge is accepted by just you can see here the edge from 1 to 5 is minimum. You have selected 1 to 5. Next 2 to 6, the edge 2 to 6 is selected and then select the edge with the lowest cost. 1 to 3 is selected. Find 1 is equal will result in 1, find 3 will result in 3. Union of 1 comma 3 will result in f is equal to 1 to 3, 2 to 5, 6 and 4. 3 edges are accepted. Now just look here one more time in this graph. The edges 2 to 5 with the minimum cost, 2 to 6 with the minimum cost and 1 to 3 with the minimum cost is selected. Then minimum cost is 6 to 5, which will result in forming a cycle. Hence you are rejecting the edge from 6 to 5 and choosing the next edge, that is 3 to 4. You can see here you have 2 to 1, 1 to 5. Next you chose 3 to 4. Next you are choosing 4 to 5, which is minimum cost is 4. Then finally you have got the minimum cost spanning tree, that is the total cost of the spanning tree is 1 2 3 is 1, 3 to 4 is 3, 4 to 5 is 4, 8 9 10. The total cost of the spanning tree is 10. By using the implementing the Kruskals algorithm, you have found the minimum cost spanning tree. That is, the Kruskals algorithm is built from forest by choosing the lowest cost edges. So you can see here, initialize forest. You are analyzing the Kruskals algorithm, and the time efficiency of initializing the forest is big O of n, and initializing the heap is big O of m, and loop performed m times. In the loop, one delete min, so big O of log m to find each big O of 2 find, and one union is used, so the worst case time complexity was big O of m log n. In fact, Kruskals algorithm has a tendency to run faster since graphs may not be dense and not all the edges need to be looked at in determining the operations. This is the time complexity of both the Prim's algorithm as well as the Kruskals algorithm.